Okay, so this course does not have a final exam, but I will ask you to make a presentation at the end of the semester. So at first, I would like you to submit the final project plan, and it's due on April 1st. So it's a little bit early to make it, but maybe you can start thinking about what kind of data you want to use for what objective. So we will study the more statistical techniques until April 1st. So you don't really have to develop the plan, this week, but I just want to give you a heads up. And the project plan is, okay, so at first, I think that many of you have already taken one of my applied statistics course. So I think that Colin, you have taken one course, right?
Yeah, last semester I was trying to predict grades, like kids' grades based off their like family situation. It was fun.
Okay, yeah, I think that's a good project. So that it's good to have such the meaningful objective, and also the many other students. I think there are maybe. I'm not sure about the Raymond, but
yeah, I did a 50-30.
Oh, 50-30.
My final
okay,
yeah, my final project there was trying to predict the cost of a.
Sorry, the cost of what?
The cost of yachts or boats based on
Okay, I see.
Boat and a bunch of other variables.
Okay, what data source did you use?
It was one of the, I think it was one of the free ones. I forget which one it was, but it's one of a website that has a whole bunch of data sources.
Oh, I see. Maybe the UC Irvine or.
Yeah, one of those.
Maybe. And also I think that Jacob also made a presentation last semester. I think you made 2 presentations, right? So in 2 different courses.
Yeah, I made one for 50-30 and one for 68-40. I ended up using the same data set for both, though. It was for a lab that I work with at Wayne in ecology.
That's great. Yeah. Yeah, so I think that some of you have already made the presentations, and so basically, at first, I would like to make sure that you are on track for a successful final presentation. So that's the objective of project plan. So project plan is just 1 to 2 page summary of the presentation. So you don't really have to make the entire project by April 1st. So at first, plan by April 1st. And if it looks good, then I just said that I just make just small comments, then you can start the project. Yeah, and the presentation is a 12 minutes presentation, and so this time I think that we are synchronous class, so that maybe I can ask to share your screen to make a presentation. So basically, you need a PDF file, to make a presentation, and you don't have to make it for now. So you only need the summary for April 1st. But finally, you are going to make the presentation file of maybe 10 to maybe 20 slides. And I will ask you maybe 12 minutes presentation. So this time the number of students are a little less, so possibly the 1 or 2 minutes longer, but basically 12 minutes presentation, maybe plus maybe 2 or 3 minutes of questions. So we have 75 minutes lecture. So probably I will push maybe 4, maybe 5 presentations per day. Maybe 5 is a little tight, maybe 4 or 5. Then yeah, for the last 2 days at least, we use it for the presentation days. And attach the data sample in additional pages. Okay, so this is for the instruction 2 years ago. So, but now that you can submit online, so either the additional pages or in Excel file. or a CSV file. And the plan will not be graded, but will be returned with comments. So students may be asked to submit a plan again if the project is not well planned. So the typical, oh, maybe, yeah. So the typical case that I ask students to resubmit the plan is the data set is not good to analyze. So basically, the data set has already been summarized. Then you cannot investigate the data. For example, that we have maybe the 10,000 the patient's data for maybe the 10 other variables, maybe some demographic variables or the medical measurements. Then if you only have the table of the summary, for example, the variable x1, maybe, okay, so age and the weight of the patients and the maybe some other, okay, so BMI and also maybe some measurements such as maybe blood pressure or something. Then if, okay, so we have the malignant group and the benign group and the, okay, so suppose we only have the average of these. This is 40.1, so this is 35.7, and the weight on average 180 pounds and 165 pounds and so on. Then we cannot really analyze this data because this table has already been summarized. So sometimes the students choose this kind of data and okay, so we have the 10,000 observations, so that's fine. But actually you don't have the raw data. So if you only have this table, you cannot summarize this data anymore. So don't choose the summarized data. So we need the raw data set. So what's the sample unit? If sample unit is a patient, we need each patient's numbers. So probably that is the most important point. And another case that the project plan has some problems is the data structure is too complicated. For example, you download the data of daily temperature in several cities for 365 days. Okay, so 365 days. This is 1 year and a good number. But if we think about temperature on January 1st and the January 2nd in the same city, those are highly correlated. So we cannot really deal with the data as independent measurements. So we have some dependent structure. So that kind of data is harder to deal with. So if you have studied time series or some other technique to deal with dependent data, maybe it's good. But for this course, mostly we deal with independent observations. So I highly recommend you to choose the independent observations. Okay, so yeah. So not entirely independent sometimes, even if you and I are somewhat related, if we think about the origin of the human, but mostly I would suggest you to use the independent data. Yeah.
Sorry, Professor, by independent data, you mean that ourselves collect our data?
Oh, I mean, I'm thinking about observations. So observations are independent. So not two observations are not highly correlated to each other.
Okay.
So like the daily temperature data, we have 365 observations. So suppose that okay, so you are thinking about someone's blood pressure and the daily temperature. And okay, so blood pressure and the daily temperature are somewhat related. And you have data for 365 days. But if we think about January 1st and January 2nd, and then probably your blood pressures are somewhat similar and the daily temperatures are also somewhat similar. So even if you have 365 observations for these two variables, we cannot deal with those observations as independent observations. It's different from 365 different people's blood pressure in different cities. So for this kind of data set, the same measurements for the 365 consecutive days, so that is harder to deal with. So I would suggest that the data set which include independent observations. So for example, patients data, 10,000 patients are regarded as independent, so that's fine. Or the sample unit may be the state of the United States. Then, yeah, it's somewhat dependent, but it's meaningful to deal with those 50 states as the independent observations. Maybe some geographic relationship, maybe the number in Michigan and the number in Ohio are somewhat similar if we think about, for example, the percentage of the obesity or something, but still it's meaningful enough to deal with that data as 50 independent observations. Okay. And some tips: set the meaningful objective in the real world, and collect or make a feasible plan to collect data. So meaningful objective in the real world. So I highly recommend you to collect the data from the original source. For example, if you analyze some county level data, maybe the Census Bureau have some data sets. Usually individual data is sometimes hard to get, but yeah, if you bring the data from your research in another department, then that's also good. Some people, some students, they bring the data from their job, and that's also good. And yeah, and so yeah, you can also bring the data from the data repository, such as the UCI data archive. Oh, maybe I have to discuss the data source later, but such as the UCI data archive something, but the set meaningful objective, not use the same objective as the data competitions, the specification. For example, you can use the Kaggle data set, but if you set the same objective as the data competition as Kaggle, then already there are a bunch of existing code available on the website. So sometimes I don't allow that, and I don't specifically prohibit using this data set. But if you use the first source, it's good. For example, Michigan Department of Education have the academic data, maybe test data. I mean, the students, the test scores from each building in the past few years. And that kind of first source data is the more interesting. Some students download the data from the CDC, the Center of Disease Control, or and one student really liked the bars, so I think she downloaded some data from some website. I don't know, probably national website. So that kind of data are more interesting. And the not too complicated data. So okay, so this is data science class, but if the data size is more than 1 million, probably it's not really easy to deal with. Even if you are a computer scientist or a software engineer, a lot of data, that means the more irregular data, observations. So that it takes more time to clean the data. And even for a simple procedure, it takes more time to run. So I don't suggest the too large data. Maybe 100,000, fine. But the more than 1 million, there you have to be very, very careful. And the number of predictors, yeah, we have studied some methods to deal with large number of predictors. So maybe 300 predictors can be dealt with those methods. But if too many predictors, also the too many irregularities, maybe two variables are too similar, or one variable is almost always 0, except for maybe 3 observations or something. So that kind of predictors are harder to deal with. Also, more predictors, usually data sets have more NAs, so maybe it's harder to deal with. And you can combine several sources, but if you combine, for example, country level data from United Nations and the World Bank and the each country's website, then that may be too complicated. So more than 3 data sources may be too complicated. Maybe 2, it's good. Maybe 3, maybe possible. But anyway, so this is a short-term project. So don't use too complicated data. Yeah, and also consider how clean the data are. If you bring the data from your research, maybe it's more irregularities, duplications, NAs, and the outliers, and some others. Yeah, so missing data, duplicated data, and the recording errors, you have to be careful about it. Yeah, so data set with independent observations is ideal. So last semester, some students suffer from the analysis because they use the time series data. So if you really have a clear idea on how to analyze it and how to remove dependencies between observations, then that's fine. But my suggestion is that use data set with independent observations, not too much dependence within the data set. Yeah, so that is what, yes. Yeah, and yeah, of course, this is the statistical course. So the consider statistical models which are appropriate for your research question and the data. So sometimes the students just don't have an idea about how to do the project. So they choose some data set, but they just copy and paste the sample project plan. And for example, classification method cannot be applied for a regression problem, obviously. So you have to choose the appropriate technique. Yeah, so in regression problem, okay, so at first, what is your problem? So you wanna summarize the data, or you wanna do regression, or you wanna do classification, or you wanna do some testing. At first, you have to have a clear idea on what kind of analysis you wanna do. If regression, what kind of models you wanna use? Maybe you do polynomial regression. Would you include the maybe the cross terms, or maybe higher order terms, or do you use lasso, or those ideas you have to consider. Yeah, and of course, don't copy the projects from other maybe on the website or something. So so these days the the Canvas has functionality to decline the copy from the internet, so we can check. I can check with that. So yeah, and the evaluation. Yeah. So so finally, we evaluate the presentation at the end of the semester, and basically the baseline is 80 points. So if you make a successful presentation, then you will get 80 points out of 100. And remember that the 80% is basically a threshold for an A. So that means as long as you make a successful presentation and you do well in other quizzes or something, then you should be fine and you can get an A. And but yeah, but of course, if the data have crucial errors, or analysis have crucial errors, or presentation may not be very good, then you may have lower score. But in the past, a majority of students get 80 points. I would say maybe, yeah, in some semesters, all students get 80 or more. In some semesters, maybe 8 out of 10 students get 80% or more. Yeah, at least majority get 80 or more. And outstanding presentations, at most 35% of classes will get 10 to 20 additional points. So this is a kind of special, bonus credits. So if everyone gets the 100, then it doesn't mean, so it doesn't appreciate the excellent presentations. So that's why I make the 80 as a baseline, and the outstanding presentations, you will get 10 or 20 more credits. Yeah, and what's the criterion? So generally, presentation and the quality of analysis, but I put the two. So there are two important points that, in addition to the quality of the presentation. So one is the quality of data and the appropriateness of the data, methodologies. So if you use the original data, I mean, you get the data from the original data source, and if it's creative, then you have higher chance to get the the bonus credits. So suppose one student gets the data from Kaggle website, and one student collects the data by themselves from some specific website, such as CDC, then the latter student is more likely to get the bonus credits, even if the analysis is not too advanced. And also I would ask you to vote for the presentations, for the best presentation. So that also counts for the bonus credits. Yeah, so originality of data collection is important, and the quality of research question, it's important, and the presentation also important. Yeah, so this is sample project plan based on the past project by a student, but I modified it a little bit. So character recognition by 16 variables. So we have the 26 letters in English alphabet. So this is a categorization problem with 26 categories. So k is equal to 26 categorization problem. So if we have some data set for English alphabet, each observation is one letter, then we can do classification, maybe by linear discriminant analysis or QDA, quadratic discriminant analysis, and the nearest neighborhood, and the multiple logistic regression, the multinomial logistic regression. So the project uses the UCI, the data. So it's not optimal, but the character recognition problem, probably it's hard to get the original data set. So that may be acceptable. And then we discuss some methodologies and how to optimize parameters, maybe by 5-fold cross-validation. And okay, so describe the data set. Maybe this data set have 20,000 observations. So 16,000 may be used for training, and remaining 4,000 as the test set, and use the 5-fold cross-validation. Yeah, then we compare the models, LDA, QDA, KNN, logistic regression. So if you are a graduate student, maybe it's good to compare at least the performance of 2 different models, for example, LDA and KNN. So then you can see which method works good for your data set. Yeah, of course, for undergraduate students, of course, you can compare methods, but for graduate students, especially PhD students, I highly recommend you to compare more than one method. And how to summarize data, you can set a plan. We have 26 categories. So we have the correct label A to Z and the predicted label A to Z. So we have matrix. Yeah, contingency table. Maybe the true this is the actual letter. Then we have the, maybe we can put probability. Okay, maybe 90% of A's are recognized as A, but maybe 5% are recognized as B, and 1% recognized as C, or something like that. So how to summarize data. So you can plan the project. And if you are not sure if you can run the project, for example, you want to collect all data set, but you have to go through the many pages of the website. Maybe you are not sure if you can collect all data sets, so maybe you have to compromise with a smaller data set or something like that. And in this case, yeah, go ahead.
Sorry, Professor.
Yep.
Do we have to develop our models in R? Can we use other programs?
Yeah, you can use other programming software. So I recommend you to use R, but if you are familiar with the other software for specific models, that's fine. And I would ask you to submit the code anyway. So it's not the most important point, but yeah. So you can use other languages.
Okay, thank you.
Yeah, so backup plans or maybe the challenging plans. You don't really have to put all items, but at least put the objectives, data description, and the methodologies, analysis plan. So at least put these items. So these are, optional. Okay, so these files are all available in Canvas, so that you can look and see. So in this case, maybe 26 categories, it may be harder to deal with. And actually, this student just analyzed A and B. So this was originally the project in the Stat 5030 by a PhD student 10 years ago. And he used A and B. So that class does not cover the categorization, the classification problem with more than 3 categories, more than 2 categories. So he chose A and B. So developed logistic regression model to distinguish A and B. Yeah, so you can develop a plan. So maybe A and B are not too hard to distinguish, but for example, maybe H and K may be similar, right? Or maybe O and Q are similar, or maybe P and F are similar. So you can think about it if you wanna pick some specific letters rather than all 26 characters. Then some data description. So this is actually from the data website. So that we have the description of the data, and it's very clean data. So this is basically the gold standard. Which letter? The letter, the actual letter is A, B, C, or Z. And the x1 to x16 are actually the variables. So actually, this is not the raw data set. Originally, the data are in a pixel, but this is not the data like that, and it's summarized data. So that we have pixels, maybe, I don't know. So we have these kind of pixels. And okay, so suppose A means probably A is like this, right? A is maybe one more. Okay, so maybe A is this letter, right? And this summarizes okay, so this is A. So, but these this data set only they have the summarized information. So the X box horizontal position. So I don't know X box horizontal position, but the probably maybe the not the mean. So I'm not sure about the horizontal position, but the yeah yeah I don't know the width, maybe for example the x3 the width of the box, probably that means the from here to here, right? So maybe the some letter such as I has the the smaller width, and the maybe letter such as Z has the wider width, and A probably the full length. So just when we see the A uses the all columns of these pixels, then at least we can recognize that is not I. So these are summarized data. So that we have the 16 variables, and we will see these 16 variables can distinguish A to Z. And this is actually this data set is not handwritten characters, but the fonts, different fonts. So it's probably easier to recognize compared to handwritten letters. But okay, so this is the data description and the actual data. Sorry, so I think I made a mistake to make a file, but yeah, so attach the spreadsheet here. Then I can see how data looks like. Okay. Do you have questions so far on final project plan? Yeah, so I will. So the sample files are available on the website. So I picked, I think, the 5 good presentations from last year. So all of the presentations get some bonus credits, either 10 points or 20 points. So it's better presentation among the all presentations. So this is the forecasting performance comparison on ILPD. ILPD is Indian liver patient data set. So this is from public data set, and he used several techniques to compare the forecasting performance of this disease. So this is the yeah. So he have, I think, maybe how many slides? Maybe I can go through. Yeah, so data description, correlation between observations, and the data summary, and yeah. So I suggest not to use the R code in the presentation file. So just make more beautiful and easy to read tables. And if you use new methods not discussed in the class, then you can explain the methods. He's really good at explaining new concepts in very short time. So that is one reason that he got the result. He got the bonus credits. ROC curve, we did not cover it. Sorry, I taught several courses. So ROC curve, maybe we haven't covered it. So you can briefly discuss.
We
Sorry?
cover ROC curve.
We covered. Okay,
yes.
That's good. Yeah, I think I covered, but I have several courses, so I wasn't really sure. Okay, and the good thing for this presentation is that he compared different methods in terms of accuracy and sensitivity, specificity, and precision. So in this case, the KNN is the best for accuracy. For precision, the 94.8%, this is maybe highest. The sensitivity, and this is highest. So depending on the criterion, these have different accuracy, but the he used accuracy as the criterion. So basically, I think this is binary problem. So that actual and predicted, and actual is malignant or benign, malignant or benign. And accuracy is, okay, so say this is the, this is the true positive, and this is the false negative, and this is true negative, and this is false negative. So the accuracy is TP plus TN over the summation. So TP, TN, FN, FP. So in terms of accuracy, he concluded that the KNN is the best. And also he compared ROC curves and compared the result and so on. So except for some trivial pages, he have probably about 15 pages. He didn't put much information in one page, so that's short enough. Probably he explained several concepts, so he spent some time. I think probably he didn't use the full 12 minutes, maybe slightly shorter. So this is one example. And this student, she likes bars. So yeah, so she downloaded the data set from the, I don't know, this USGS, North American, the breeding bird survey. And yeah, and you know, more fancy illustrations and the graphics and the introduction of the data set. Yeah, so she even put some pictures. Yeah, so this decreasing bars, actually we haven't seen, oh, maybe I see this bird so often. So this is a kind of aggressive bird, which is annoying. But yeah, so yeah, I think we have seen this one and a lot of these Canadian goose and so on. Yeah, so yeah, some presentation looks much nicer, fancier. I mean, but I think that in terms of statistical models, the last presentation, the Honjian's presentation, they discussed more comprehensive analysis. So yeah, you can look and see the 5 different presentations. You don't have to mimic the presentation, but those are good presentations. Yeah, some are by undergraduate students and some are by graduate students. How many undergraduates? Any graduate students in this class this semester?
Yes, I am graduate.
Okay.
Me too.
Okay. I see. So maybe at least a few graduate students. Yeah, I don't really distinguish the undergraduate and the graduate students. But the graduate students, that it's good to have to compare the more than one method. Okay, so these are the final projects. Do you have any other comments, questions, concerns? And without submitting final project, you cannot get course credits. Okay, so you do all quizzes correctly, you got perfect in the midterm, and you missed final project, then you will not get credits. So just make sure that you can submit the project. So just you only have maybe 1 or 2 weeks, maybe 2 weeks to do analysis. So, and also you are taking other courses. So just make the project manageable.
Sorry, Professor, when is the deadline for submitting the project?
Oh yeah, projects that we haven't decided the schedule. So after the spring break, so we decide which students that make which presentation and presentation on which date. But yeah, the deadline is likely to be the last week of the lecture. I mean, you have to make a presentation in the last week of the lecture. So syllabus is not here. Oh, syllabus here. So, okay, so here. So we have the 9 students here, maybe 8 here, maybe 8 or 9 students here. And one more student will make a presentation from another class because I thought that it's useful for you to listen to. And so, yeah, so this one. So your presentation is likely to be April 21st, 26th, or 28th. And only 9 students. So possibly we put all presentation into these 2 days, 21st and 26th. So, possibly 28th. So I review the final project plan for the presentation on 21st at first. Then after that, I review the final project plans for 26th and possibly 28th. So these are the deadlines. So after the presentation, then you have to submit the file. So the deadline is just after your presentation. Submitting deadline is just after the presentation. And you don't have to revise the presentation file even if you got comments during presentation. Okay, so any questions? Yeah, I think this is very good experience for you because the mathematics that you have to study a lot of things and that you don't really have a final project in many courses, even at 5,000 level. But for applied statistics, you can learn methodologies, then you can apply that to the real world problem. So that is time consuming, but the fun part, I believe. Okay, so yeah. Okay, so if you don't have questions, we continue the chapter 6. I have some problem in iPad to control. It does not scroll. Yep. Okay, so remember that we have studied several dimension reduction methods. One is the principal component regression. And the other is partial least square. So both are similar in terms of the idea. We want to summarize the information by lower dimensional space. I mean, we summarize the large number of predictors into small number of summarized information. So x1 to xp, we summarize this into z1 to zd. And these, of course, are much smaller than p. And the difference between PCL and the PLS is that we use the information of y for PLS. PCL, the summarizing part, dimension reduction part, and the regression part are separated. PLS, it's combined. So PLS is somewhat ad hoc because we use the information of y to find the best, the predictors. So PCR may be more what the so PCR doesn't use the information of Y to summarize X. So that's the difference. So at least the PCR is a fair method. So PLS makes some trick, but logically it should work better because we use the information of Y to summarize this data. So the way to summarize the data is more optimized to predict Y. And both methods can be dealt with the PLS package. I don't know what PLS means, partial least square. I don't know, maybe, but also it includes the PCR. Okay, so at first, PCR, how to apply the PCR. And okay, so we use the hitters data. This is the baseball batters data in ISLR package, and so this is the data set. So we want to summarize, okay, so we want to predict salary by several performance measures. So these performance measures are highly correlated. For example, home runs. Yeah, I don't know, but yeah, usually the home runs and the number of walks, these are correlated. Right. So the many variables are correlated, and we want just the general performance measure to predict salary. So logically, it makes sense to summarize the variables to predict this salary data. And we use the PCR function. So this works just as a regression model. So just the salary is Y, and the dot is the other variables. So we predict or we explain the salary by other variables. And we specify data set and the scale. So scale means if scale option is equal to true, that we make the standard deviation of each variable equal to 1. So remember that when we do principal component regression, usually we have to standardize variables. Otherwise, just a variable with large variation is chosen as the principal component. So that does not make sense. And also, if we don't standardize, actually the regression result that depends on the unit of each variable, which does not sound good. So we standardize it so the scale is equal to true. Also, we can specify center is equal to true to make the mean equal to 0. Yeah. And the sum validation method, how to choose the number of principal components. Then we use the cross validation. You can see the help of this PCR to see other options. And validation plot and the PCR fit, so this object. And validation type, the mean square error. Then this. So this is the test. I mean, in this case, cross-validated the mean square error by number of components. So we fit the salary on first principal components to maybe these components, then number of components is D. Yeah, so we have error term, but okay, so this is the regression model, and this is D. So larger D, we have more information, but yeah. So, but sometimes if D is too large, then the test performance, the cross-validated performance, the mean square error gets larger. And actually, after 5, it's almost flat. And I think technically the 7 is smallest here. It's really hard to see, but yeah, but if we see this, the summary of this, the regression, you can actually see how large the cross-validated error is. And we have the two numbers, the cross-validation CV and adjusted CV. So adjusted CV that adjusts the basically the number of observations. So cross-validation uses the smaller subsets, right? So only 90% of observations as training set. So that makes error size a little larger. In fact, we have, the 100% of data. So we only use 90% to train the model. So adjusted version, actually, it adjusts the effect of the smaller training data set. And it also affects the relative size of the cross-validated MSE. So the red one is adjusted one, but mostly similar. So CV is the usual CV, and adjusted CV is it considers some factor consider the fact that we use the smaller training data set. And you can see that the smaller CV is better. So okay, so in terms of the usual CV, I think this is smallest, the 345.4. This is smallest. Others are larger. 300, almost similar here. But usually, if it's too similar, we would go for smaller number of components. So yeah, I think it's fair to choose the 7 components here. Maybe even some people use maybe 5 or 6, maybe 5, almost the same. Yeah, so theoretically, maybe 7 is the best. And the adjusted version, actually, this is smaller, even slightly smaller. So yeah, there are several criterions. So it's not 100% clear, but probably 7 is sufficient. And this is the percent of variance explained. So in terms of the variability, how much variability it has. So if the Z1 has the variance of, okay, so suppose that we have the P predictors and the variance of Z1, I don't know how many predictors are there, maybe 18. So variance of Z18. So this is, okay, so 100, and this is 10, and this is 5, and so on. Then, okay, we take summation. Suppose the summation is S, then 100 plus 10 over 10 over S, sorry, S. So this number is here. Sorry, X, yeah, so this number is here. And this one, the 41.58, I mean, in terms of percentage, so maybe I would say times 100. Okay, so, and the salary, so this is the variation in salary. So the variance of salary, so this is the entire amount of variation, and the if we divide the variance of the error in the prediction model, that is salary on Z1 and Z2, okay. And if we subtract 1 minus this, so this is the this number. Okay. So 41% of salary is explained by Z1 and Z2. 41% of the variation in salary is explained by Z1 and Z2. Yeah. So you can see that, for example, if we use maybe the 13 components, then anyway, the 99% of variation in Z, variation in X is explained by Z1 to Z13. So you can see that the other maybe 6 components are probably almost useless. Anyway, it includes most information. Yeah, and you can see that even if the number of components increases, the maximum we can do is maybe the 54%, 55%. So we cannot explain more than that. So if we use the 7 components as suggested by cross-validation, we explain the 47% of variation. Even if we use 19 all variables, still the 55%. So yes. And this is for training set. So yeah, so more components, we can explain more. But even we increase the number of components from 7 to 19, still the increase isn't really the dramatic. Maybe 47 to 55 is large, but in terms of cross-validation, the 7 is better than 19. Any questions? So the next one is the partial least square. So we use the information of salary to summarize the Butler's performance information. And PLSR, the principal, partial least square regression, PLSR, and the salary on other variables. And this is data set, and the scale is true, validation CV. So just the same, just this name of the function is different. Then we can make the same graph. And now you can see that maybe 11 is the best, maybe 12. So this is the cross-validated mean square error for number of components, D. And you can see that in terms of the cross-validation, the smallest cross-validated error is maybe 346 point. No, actually this one is better. So 12 is the best. So this is the best point in terms of the black line. So adjusted version, probably it's similar. So this is the best. Maybe 11 is the best, but the yeah, slightly different criterion. Gives slightly different D. But probably D is equal to 11 or 12 is the best. So 11. And with 11 components, basically the Z1 to Z11 includes 97% of the information. And it explains the 54% of the entire, so 54% of the variance in salary. So we could explain 54%. And the 11 components include 97% of information. Maybe we can compare this with the previous result. Maybe we can use just the 12. Okay. Then you can see that this number is larger for PCR because PCR is optimized to increase this number. So this number is larger than the PLS, the partial least square. Partial least square, I think this is, yeah, 96.68. So actually 2% larger. So it's pretty large. But in terms of prediction power for salary, this is 48%. And this is 54%. So this is much larger because the PLS is optimized to maximize this number. Yeah, so yeah, generally PLS has better performance criteria. I mean, the better performance for prediction, but the you have to be careful that we have to use at least cross-validation to optimize it. So if you arbitrarily choose the number of components, then sometimes it overfits the situation. PLS, yes, yeah. Yeah, so this is the chapter 6. So yeah, it's already 8:05:45. So do you have any questions? If you don't have, we go to chapter 7. So logically speaking, the PLS sounds better for prediction. But of course, it depends on the data. So you can try both methods if you have the real data. Yeah, so even if the logically PLS works better, still, it's not clear the practically which is better. For example, if the relationship between X and Y is not stable, so for example, the relationship between, okay, so relationship between the, yeah, so two variables are sometimes not stable. I don't know what's the best example, but for example, general business condition and the stock price of the ExxonMobil, those are really highly correlated before COVID. But after COVID, the people stopped driving cars, and even if the ExxonMobil's profit is down, but still the condition of economy isn't that bad. So the relationship between Y and X breaks sometimes. So in such a case, the PLS is more fragile, right? Because we use information of Y to summarize X. So in real situation, it's not clear which works better. Logically, if the relationship is stable, the PLS sounds a better way. Okay, so that's it. Any comments or questions? Okay, so chapter 7, I think we only can almost preview this, but still we have 10 minutes. So moving beyond linearity. So traditionally, we start with the regression model, y is equal to beta naught plus beta 1x plus epsilon. And this is so-called a linear model. And you can estimate the beta naught and the beta 1. So this is the simplest statistical model to explain y by x. So it doesn't mean x causes y, but at least x explains y. So this is linear in two meanings. So the first meaning is that this is, the linear function, beta naught plus beta 1x. This is a linear function of x. But the second point is that this is linear in beta naught and beta 1. And actually, when we say a linear model, so the second one is more important. Because statistically, the topic is how to estimate beta naught and beta 1. So for example, even if we have square here. Okay, so then it's not linear in terms of x, but still it's linear in terms of beta naught and beta 1. And statistically, our objective is to estimate parameters. So it doesn't matter whether this is x or x squared. So, okay, so this is the most basic model. But in terms of x, we can go further like this. Still, this is a linear function of beta naught, beta 1 up to beta d. So this is called polynomial regression that we have already studied it. So this is one, at first we can do this to extend the model. Polynomial regression doesn't work well usually. If you do final project, then except for time series data, it's really hard to find an example that the relationship between x and y is nonlinear, I mean quadratic or cubic. It's hard to find it. So once one student tried to explain the age of baseball players and the number of home runs. So number of home runs depends on the power, and usually the prime age of professional baseball player is around maybe 28 to 30. So he expects the graph looks like this, but it doesn't really go well. So usually the quadratic function that can find some optimal point. So for example, this is the tax rate and the tax revenue. If tax is too high, the economy collapsed, then tax revenue actually goes down. So we expect the similar kind of pattern, but usually it's hard to detect this quadratic curve. So in reality, sometimes it's hard to find the good example to apply polynomial regression, but at least it works. This is more general one. And actually, this is the one thing the polynomial regression worked well. So this is age, and this is the wage. Then I think in the United States, maybe 45 years old to 50 years old, that it reached the maximum wage. So we can fit for example, the quadratic curve to identify this pattern relationship between wage and age. The right-hand side, this is just a histogram. The age and the probability of wage is more than 250, probably $1,000. Yep. So the next one is the step functions. So we can just fit the level for each interval. So especially if the observations have, for example, this kind of pattern, it's good to identify the threshold, the C1, identify the threshold C2, and we fit straight line here, here, and here. Then it looks, it fits well. So this is Y and this is X. So we have the step functions, the C0. This is the actual indicator function for X is less than C1, and indicator function for between C1 and C2, and indicator function of the X is more than CK. Then this model, estimating beta naught to beta k, this is linear. So this equation is linear in terms of beta naught to beta k. But the difficult part is how to choose this C1 to CK. So that is hard. So there is difficulty to determine the knot points C1 to Ck. So this estimation is not as easy as linear regression. But if you, just to change the threshold, then certainly we can fit. And this is the same same data set as the last one. So that in this specification, our conclusion is that the wage is lower until the age 32 or 3. Then wage gets higher between 32 and maybe 63. Then after that, wage gets lower. But identifying this point, these 2 points, so this is not easy. And also we have to decide how many knot points. We have the 2 knots or 3 knots. That is also a problem. Yeah, I think it's already 8:15. So we stop here. Then next time that we discuss the more advanced method to model beyond linearity.
Thank you. Take care.
Yes. Okay, so yeah, if you have questions, you can stay online. Otherwise, see you next week. Next week is spring break.
Yeah, have a good break.
Yeah, you too.
Good break.
See ya.
Thanks.
Bye.
Bye.
Thank you, Professor. Have a good break.
Oh, sure, you too.
Have a good break, Professor.
Oh, you too.
Thank you.
Thanks.